Today we'll talk about another method of learning called learning by correcting mistakes. An agent reaches a decision. The decision turns out to be incorrect or suboptimal. Why did the agent make that mistake? Can the agent correct its own knowledge and reasoning so that it never makes that same mistake again? As an example, I'm driving and I decide to change lanes. As I change lanes, I hear cars honking at me. Clearly I made a mistake. But what knowledge, what reasoning led to that mistake? Can I correct it so that I don't make the mistake again? Learning by correcting mistakes is our first lesson in meta-reasoning. We'll start today by revisiting explanation-based learning. Then we'll use these explanations for isolating mistakes. This will be very similar to diagnosis, except that here we'll be using explanation for isolating mistakes. This will make it clear why explanation is so central to knowledge-based AI. Then we'll talk about how we can use explanations for correcting mistakes, which will set up the foundation for subsequent discussion on meta-reasoning. To illustrate learning by correcting mistakes, let's go back to an earlier example. We encountered this example when we were discussing explanation-based learning. So imagine again that you have bought a robot from the Acme hardware store, and in the morning you tell the robot, go get me a cup of coffee. Now the robot already is bootstrapped with knowledge about the definition of the cup. A cup is an object that is stable and enables drinking. The robot goes into your kitchen and can't find a single clean cup. So it looks around. This is a creative robot, and it finds in the kitchen a number of other objects. One particular object has this description. The object is light and is made of porcelain. It has decorations and it has concavity and a handle, and the bottom of this object is flat. Now the robot decides to use this object as a cup because it can prove to itself that this object is an instance of a cup. It does so by constructing an explanation. The explanation is based on the fact that the bottom is flat, that it has a handle, that the object is concave, and that it is light. Let us do an exercise together that will illustrate the need for learning by correcting mistakes. So shown here are 6 objects, and there are 2 questions here. The first question is, which of these objects do you think is a cup? Mark the button on the top left if you think that a particular object is a cup. The second question deals with the definition of a cup that we had on the previous screen. So mark the button on the right as solid if you think that that particular object meets the definition of the cup in the previous screen. What do you think, David? Which one of these is a cup and which one of these meets the definition of the cup on the previous screen?
So according to my intuitive definition of a cup, 3 of these objects are cups. The object in the top right is not, because that's a potato masher. The object in the top left isn't, because that's a little pail. And the object in the bottom middle is not, because that's actually a candlestick holder. According to the definition of a cup that the robot was bootstrapped with, however, only the potato masher doesn't meet the definition. All 5 of these objects have flat bottoms, they all have concavity, they're all light, and they're all liftable. We might not think that the candlestick holder is liftable because it doesn't have a handle, but we might also think that it's liftable because it's light enough, so either way would work for that. But it's clear that the pail up here meets all our definitions for a cup. But it's clear that the pail meets all our requirements for a cup, but is not actually a cup.
Let us build on David's answers. Let us suppose that the robot goes to the kitchen and finds this pail in the kitchen. It looks at the pail and decides that this pail meets its definition of a cup, denoted here by the solid circle. The robot brings water to you in this pail. You look at the pail and you say to the robot, "No, robot, this is not a cup." At this point, you would expect the robot to learn from its failure. Cognitive agents do a lot of learning from failures. Failures are opportunities for learning. We would expect robots and intelligent agents more generally to learn from their failures as well. How then may a robot learn from the failure of considering this pail as a cup? Note that the problem is not limited to this particular pail. We can take a different example connecting with this particular cup. Imagine that the definition of cup included the statement that it must have a handle, in which case the robot may not recognize that this is a cup. Later on you may teach the robot this in fact is a good example of a cup because it's liftable. In that case, the robot may want to understand from that failure, it may want to understand why did it not consider it to be a cup. It should have considered it to be a cup. So the problem is not just about successes that turned out to be failures, but also about failures that should have been successes. So the question then becomes, how might an AI agent learn from its mistakes? Learning by correcting mistakes or learning from failures really entails answering three separate questions. The first question is, how can the agent isolate the error in its form or model? So the agent had some model of the world, it made a mistake based on its model. How can it identify the error in its model? Note that this particular problem is very closely connected to the question of diagnosis that we discussed earlier. The second question is, how can the agent explain to itself that the fault it has identified, the error, in fact led it to the problem, to the failure? Having identified the fault and explained how the fault led to the failure, the third question is, how can the agent repair the fault in order to prevent the error, the failure, from reoccurring? You may have noticed that earlier we had related learning by correcting mistakes with metacognition. You can see how that relationship occurs. The agent has some knowledge of the world. That knowledge leads it to failure. The agent is using that failure to repair its own knowledge. It is as if the agent is looking into itself, looking into its own reasoning, into its own knowledge, and correcting itself. Note once again that the learning here is incremental. We are learning from one example at a time. However, instead of simply learning from an example, we are also using explanation-based learning. We are trying to explain why a particular fault led to a particular failure. That explanation connects then with explanation-based learning, not just with the notion of incremental learning. Let us see how these three questions occur in the example of the pail. The first question is, how can the agent identify that the fact that this particular pail has a movable handle, not a fixed handle, is why this is not a good example of a cup? The second question is, how can the agent build an explanation that proves why having a movable handle makes this a poor example of a cup? Why does that lead to a failure? The third question is, how can the agent change its model of a cup so that it never again picks an object with a movable handle as an example of a cup?
So when we talked about explanation-based learning, we used another example of this as well. We imagined a desktop assistant that I can just say, hey, fetch me that important file from last Tuesday, and it can construct its own understanding of what file I might be talking about. It has a notion of what files have been important in the past and certain criteria of those files, so it constructs an understanding of what important is, and then tries to transfer that onto files from last Tuesday. Now imagine that I told this agent, hey, fetch me that important file from last Tuesday, and it returns me a file that actually wasn't important. And I say, hey, that file isn't actually important at all. The agent would first try to isolate what error it made in diagnosing that particular document as important. It might, for example, notice that every other document I've ever labeled as important was very recent, whereas this one was very old. So even though it met all the criteria for an important document, there might be more criteria that it didn't consider yet, and one of those might be that only new documents are very important. It would then explain that the problem came from the assumption that an old document could be important, and it would then repair its model to say that in the future, old documents can't be important, even if they meet the other criteria for importance.
This problem of identifying the error in one's knowledge that led to a failure is called credit assignment. Blame assignment might be a better term. A failure has occurred. What fault or gap in one's knowledge was responsible for the failure? That's blame assignment. In this lesson, we'll be focusing on gaps or errors in one's knowledge. In general, the error could be in one's reasoning or in one's architecture. Credit assignment applies to all of those different kinds of errors. Several AI theorists, Marvin Minsky for example, consider credit assignment to be the central problem in learning. This is because AI agents live in dynamic worlds. Therefore, we will never be able to create an AI agent which is perfect. Even if we were to create an AI agent which had complete knowledge and perfect reasoning relative to some world, the world around it will change over time. As it changes, the agent will start failing. Once it starts failing, it must have the ability of correcting itself, of correcting its own knowledge, of correcting its own reasoning, correcting its own architecture. You can see again how this is related to metacognition. The agent is not diagnosing some electrical circuit or a car or software program outside. Instead, it is self-diagnosing, self-repairing. As we mentioned previously, in general, the errors may lie in the knowledge, in the reasoning, or in the architecture of an agent. And therefore, learning by correcting errors might be applicable to any one of those. However, in this lesson, we'll be focusing only on errors in knowledge. In fact, in particular, we'll be focusing on errors in classification knowledge. Classification, of course, is a topic that we have considered this class repeatedly. Let us consider an AI agent that has two examples of executing an action in the world. In the first experience, the agent views this object as a cup and gets the feedback this indeed was a cup. So this was a positive experience. This, on the other hand, is a negative example. Here the agent viewed this as a cup and got the feedback that this should not have been viewed as a cup. We can visualize the problem of identifying what knowledge element led the agent to incorrectly classify this as a cup as follows. This left circle here consists of all features that describe the positive example. The circle on the right consists of all features that describe the negative example. So features in this left circle might be things like this is a handle, there is a question mark, there is a blue interior, and so on. The circle on the right consists of features that characterize a negative example. It has a movable handle, it has a red interior, it has red and white markings on the outside. There are some features that characterize only the positive experience and not the negative experience. There are others that characterize only the negative experience and not the positive experience. There are also many features that characterize both the positive and the negative example. For example, they are both concave, they both have handles, and so on. In this example, it is these features that are especially important. We'll call them false suspicious features. We call them false suspicious features because first, they identify only the negative experience. Secondly, one or more of these features may be responsible for the fact that the agent classified this as a positive example when in fact it was a negative example. As an example, suppose that this feature corresponds to a movable handle. This is a false suspicious feature. It is false because this experience was false. It is suspicious because it does not characterize the positive experience. And thus, it may be one of the features responsible for the fact that this was a negative example. But now there is an additional problem. There are a number of false suspicious features here. So how would the agent decide which false suspicious feature to focus on? We have encountered this problem earlier when we were talking about incremental concept learning. At that point, we had said that we want to give examples in an order such that each succeeding example differs from the current concept definition in exactly one feature, so that the agent knows exactly what to focus its attention on. The same kind of problem occurs again. How might the agent know which feature to focus on? One possibility is that it could try one of the features at a time and see whether it will work. That is, it could select this feature, repeat the process, get more feedback, and either accept it or eliminate it. An alternative method is that the agent may receive not just two experiences, but many such experiences. So if there were other positive experiences that covered this part of the circle, that would leave only this as a false suspicious feature, and then the agent can focus its attention on this feature. As an example, just like this circle may correspond to a movable handle, this may correspond to a red interior because red interior is one of the features that characterizes the negative example and not the positive example. But later on, there might be another positive example that comes of a cup which had a red interior, in which case the agent can exclude this particular feature. Now, the inverse of this situation is also possible. Let us suppose that the agent decides that this is not a cup, perhaps because its definition says that something with a blue interior is not a cup. And therefore, it doesn't bring water to you inside this cup and tells you there is no cup available in the kitchen. You go to the kitchen, you see it, and you say, well, this is the cup. Now the agent must learn why did it decide that this was not a cup. In this case, the relevant features are these three features. These are the three features that define this cup but do not define the other experiences. So this dot may correspond to a blue interior, this dot may correspond to a question mark on the exterior. We'll call these features true suspicious, just like we call them false suspicious. These are the features that prevented the agent from deciding that this was a positive example of a cup. One or more of these features may be responsible for the agent's failure to recognize that this was a cup. Here is an algorithm for identifying what elements in an agent's classification knowledge may be potentially responsible for its failure. Let us look at the problem of identifying the false success elements. As we said earlier, Potentially, the agent may receive a set of positive experiences and a set of negative experiences, not just one positive or one negative. First, take the intersection of all the features that are responsible for all the false successes. A false success, again, is something that we identified as success but was not a success, like the pail. We identified it as a cup, but it was not a cup. First, take the intersection of all the features present for all the false successes. False success is an object that the agent identified as a success, but in fact was false. Like the pail, the agent identified that it was a cup, but it wasn't. Then take the union of the features present for all the true successes. A true success is something that the agent classified as a success and indeed was a success. Now remove all the assertions in the union of the true successes from the intersection of the false successes to identify those elements that are present in the false successes only.
So to put that differently, start off by gathering together anything that's ever present in a false success. Then gather together everything that's true for every single true success. Remove the things that are true for every true success from the things that are ever true for any false success. In that way, we get a list of only the things that are true for some false successes.
Similarly for identifying suspicious true success relationships, except that here the operations are in reverse.
So similarly, here we gather together everything that's ever true about any true success, and then gather together the things that are true for every single false success. So every single false example has these things in common. Then we remove the things that every single false example has in common from the things that are true for any true example.
As you can see, we are taking unions and intersections of features characterizing different examples. The number of examples, both positive and negative, needed for this algorithm to work well depends upon the complexity of the concept. In general, the more features you have in the description of the objects, more will be the number of the examples you will need to identify the features that were responsible for a failure. So let us look at the result of the kind of learning technique we are discussing here. Here might be the old concept of a cup. In this particular case, this particular concept definition has been put in the form of a production rule. Here is the new concept definition for a cup. This is almost identical to the previous definition, except that now the object not only has a handle, but also the handle is fixed. This is similar in many ways to incremental concept learning. You may recall that in incremental concept learning, at any particular stage of processing, there was a concept definition. As new examples came, then the concept definition changed depending on the new example and the current concept definition. Note that in this method of concept revision, the number of features in this if clause may become very, very large very quickly. Here we have object has a handle and handle is fixed. We could keep on adding additional features. The interior is blue that cover all the positive experiences. The difficulty is, at the present time, there is no understanding for why the fact that handle is fixed is an important part of the cup definition. This requires an explanation. Why is it that the handle being fixed is an important part of the definition of a cup? This is one of the key differences between knowledge-based AI and other schools of AI. Classification is ubiquitous in many schools of AI, as we have discussed earlier. Explanation, however, is a key characteristic of knowledge-based AI. Explanation leads to deeper learning. It not only says, here are the features that result in a concept definition, it also says, and here is why these features are important for the concept definition. This brings us to the second question in learning from failures. Now we want the agent to explain why a particular fault in its knowledge led to its failure. You may recall this explanation from our lesson on explanation-based learning. There the agent had constructed an explanation like this to show that a specific object was an example of a cup. For our example of a pail, the agent may have constructed a similar explanation with the object being replaced by pail everywhere. Now, however, the agent knows that pail is not an example of a cup. Something is not quite right with this explanation. We have also just seen how the agent can identify the false suspicious relationship in this explanation. It has identified that the handle must be fixed because that is the feature that separates the positive experiences from the negative experience. The question then becomes, how can this explanation be repaired by incorporating handle is fixed? Where should handle is fixed go? David, what do you think? Where should the agent put handle is fixed in this explanation?
So it seems like the most obvious place to put it would be under the object is liftable connection. In order to make it liftable to enable drinking, it needs to be fixed.
What do you think? Is this a good way to fix the agent's error? David's answer was good, but not necessarily optimal. I think he put handle is fixed at this particular place in the explanation because the first reason here. He wanted to capture the notion that only fixed handle cups enable drinking, and that this part does it. He wanted to capture the notion that only fixed handle cups enable drinking, and this certainly does that. However, this is not an optimal way of fixing this particular explanation. However, this is not the best way of fixing this particular explanation because it leads to additional decisions. It suggests that only those things which have a fixed handles are liftable. But of course, from the pail we know that the pail does not have a fixed handle and yet the pail is liftable. This suggests that handle is fixed should go somewhere else, perhaps above object is liftable but still below object enables drinking. The agent too can figure out that this is not the optimal place for putting handle is fixed because A, it voidates its notion of a pail. A pail is liftable but has a movable handle. It also voidates its notion of a briefcase. This part was coming from its precedent of a briefcase. The briefcase has a movable handle and it too is liftable. This is how the agent knows that its handle is fixed should go somewhere else in this explanation. Above object is liftable, but beneath object is enables drinking. So recall that the agent figured out that handle is fixed should go beneath object enables drinking, but not beneath object is liftable. So the agent may put handle is fixed here in this particular explanation. This is correct. If the agent has background knowledge which tells it that the reason handle is fixed is important is because it makes the object manipulable, which in turn enables drinking, then the agent may insert this additional assertion here in the explanation. Even more, if the agent has additional background knowledge that tells it that the fact that the object has a handle and that the handle is fixed together make the object orientable, which is what makes the object manipulable, then the agent may come up with a richer explanation. The important point here is that as powerful and important as classification is, it alone is not sufficient. There are many situations under which explanation too is very important. Explanation leads to richer learning, deeper learning. There is one more important point to be noted here. This again is the illustration from incremental concept learning. When we were talking about incremental concept learning, we talked about techniques for learning. We did not talk about how these concepts were going to be used. However, in learning by correcting mistakes, we are talking about how the agent actually uses the knowledge it learns. This point too is central to knowledge-based AI for several reasons. The first reason is that knowledge-based AI looks at reasoning, looks at action, decides how knowledge is going to be used, and then determines what knowledge is to be learned. It sets the target for learning. Secondly, you may recall this particular figure for the cognitive architecture that we had drawn earlier. You may see that reasoning, learning, and memory are closely connected, and all of that is occurring in the surface of action selection. This figure suggests that we not only learn so that we can do action selection, but additionally, as we do action selection and we get feedback from the world, it informs the learning. As this figure suggests, intelligent agents, cognitive systems, not only learn so that they can take actions on the world, but further, that the world gives them feedback, and that feedback informs the learning. Once again, failure are great opportunities for learning. One additional point to be made here. Learning by correcting mistakes views learning as a problem-solving activity. An agent meets failure, it needs to learn from the failure. It converts this learning task into a problem-solving task. Let us first identify what knowledge error led to the failure. Then let us build an explanation for this. Then we'll repair it. Thus, learning is closely intertwined with memory, reasoning, action, and feedback from the world. Notice also that the reasoning, learning, and memory here in the deliberation module are closely connected to the metacognition module. Here the reasoning, memory, and learning may be about action selection in the world, but the metacognition module may have its own reasoning, learning, and memory capacities. And some of the learning in the metacognition is about fixing the errors in the deliberative reasoner. So metacognition is thinking about thinking. The agent used certain knowledge to think about the action selection, and it conducted those actions in the world. Metacognition is thinking about what went wrong in its original thinking. What was the knowledge error? We'll return to metacognition in the lesson on meta-reasoning.
So how would you use learning by correcting mistakes to design an agent that can answer Raven's progressive matrices? On one level, this might seem easy. Your agent is able to check to see if its answers are correct, so it's aware of when it makes a mistake. But the knowledge of when it's made a mistake merely triggers the process of correcting the mistake. It doesn't correct it itself. So how will your agent isolate its mistake? What exactly is it isolating here? Once it's isolated the mistake, how will it explain the mistake? And how will that explanation then be used to correct its mistake so it doesn't make the same mistake in the future? Now, in this process, we can ask ourselves, will your agent correct the mistake itself, or will you use the output to correct the mistake in your agent's reasoning? Will you look at what it did and said, here's a mistake it made, so next time it shouldn't make that mistake? If you're the one using your agent's reasoning to correct your agent, then as we've asked before, who's the intelligent one, you or your agent? So today we've been talking about learning by correcting mistakes. We started off by revisiting explanation-based learning and incremental concept learning. In those lessons, we were dealing with a small number of examples coming in one by one. We dealt with the same thing here, but here we had the additional feedback about whether or not our initial conclusion was right or wrong. We then talked about isolating mistakes. This was similar to our problem of diagnosis. Given a mistake, how do we narrow down our reasoning to find exactly where that mistake occurred? Then we talked about explaining the mistake. This is key both to building human-like agents and to enabling the agent to correct its mistake. Only by explaining the mistake can the agent correct it efficiently. And after those phases, correction becomes a much more straightforward task. Next time we'll talk about meta-reasoning in more detail. For example, here we've discussed mistakes in knowledge, but what about mistakes in reasoning? What about mistakes in architecture? What about gaps instead of mistakes, where we don't know something instead of knowing something incorrectly? We'll talk about all that next time.
Learning by correcting mistakes is a fundamental process of human learning. In fact, it may closely resemble the way you and I learn in practice. In our lives, we rarely are passive learners. Most of the time, we are active participants in the learning process. Even in an educational setting like this, you're not just listening to what I'm saying. Instead, you're using your knowledge and reasoning to make sense of what I'm saying. You generate expectations. Sometimes those expectations may be violated. When they are violated, you generate explanations for them. You try to figure out what was an error in your knowledge and reasoning. This is learning by correcting mistakes. Notice that you think about your own thinking, a step towards meta-reasoning, which is our next lesson. Today we'll talk about meta-reasoning. Meta-reasoning is thinking about thinking, knowledge about knowledge. In this case, the agent is not reasoning about something outside in the world. Instead, the agent is reasoning about itself, about its own knowledge, its own reasoning, its own learning. As an example, I can ask you, what is President Obama's telephone number? I'm sure all of you can immediately tell me you don't know. But how do you know that you don't know? We touched a little bit about meta-reasoning when we were talking about learning by correcting mistakes. There we were interested in errors in the knowledge base. In journal, errors can also be in reasoning or in learning. We'll start today by talking about mistakes in reasoning and learning in addition to mistakes in knowledge. Then we'll talk about knowledge gaps, not just errors in the knowledge, but when some knowledge is actually missing. Then we'll talk about a very journal metacognitive skill which leads to strategy selection and integration. In this class, we have talked about a large number of methods, but we haven't yet talked about how an intelligent agent can put multiple methods together to address a complex problem. Then we'll discuss meta-meta reasoning, or meta-meta-meta reasoning. How far can we go? Finally, we'll discuss an example of meta-reasoning in action that is sometimes called goal-based autonomy. We have come across the notion of meta-reasoning earlier in this class. You may recall this was the explanation that an agent had built to decide why a particular object was an instance of the cup. Then we told it that it was an incorrect decision. The agent then reflected on its knowledge. Here was the knowledge, here was the explanation it had built. It is now reflecting on it and trying to figure out what makes this particular explanation incorrect. Where does the fault lie? That was an example where the agent was reflecting on its knowledge. Perhaps this knowledge was stored in the short-term memory that had been pulled out of the long-term memory. But just like there can be an error in the knowledge, there could also potentially be an error in the reasoning or potentially an error in the learning process. An example of an error in reasoning occurred very early in this particular class. You may recall this particular diagram from mean sense analysis. This was the blocks microworld. The agent needed to take these blocks from this initial state to this goal state. However, there were multiple goals here, D on table, C on D, B on C, and as the agent tried to accomplish these goals, it ran into cul-de-sacs where no further progress was possible without undoing some of the earlier goals. So that was an example of metacognition over reasoning, where the agent was trying to figure out what was the error in my reasoning and how can I remedy it. We can similarly have metacognition over learning. So an example of metacognition over learning occurred when we were talking about learning by correcting mistakes. You may recall this was the explanation the agent had built after it had remedied the explanation. The remedy in this particular case was adding here that the handle is fixed and relating it to the rest of the explanation. Given that the agent had used explanation-based learning to build this explanation in the first place, we can think of the agent as reflecting on its process of explanation-based learning and asking itself, what did I do wrong? And then deciding, well, I built the wrong explanation. I must change that explanation, and that is what learning by correcting mistakes did. We can consider this to be a process of metacognition over learning in the sense that the agent may say, how did I learn this particular knowledge? Well, I learned it through explanation-based learning. So what was wrong in my process of explanation-based learning that led to this incorrect explanation? How do I fix my process of explanation-based learning so that I do not make the same error again? So far, we have talked about the case where there was an error in the knowledge, or an error in the reasoning, or in the learning. The knowledge, for example, was incorrect in some way. But the knowledge can also be incomplete. There can be a gap in knowledge, or in reasoning, or in learning. A gap in knowledge occurred when we were doing this exercise under explanation-based learning. In that particular case, the agent had built this part of the explanation, and it also had this part of the explanation. But it could not connect these two because there was no knowledge to connect that an object that has thick sides and that can limit heat transfer will protect against heat. Once the agent detects this as a knowledge gap, then it can set up a learning goal. The learning goal now is acquire some knowledge that will connect these two pieces of knowledge. Once the agent detects a knowledge gap, it can set up a learning goal. The learning goal now is to be able to connect these two pieces of explanation. Notice that we are seeing how agents can spawn goals. In this particular case, the agent is spawning a learning goal. You may recall that when we did this exercise in explanation-based learning, the agent went back to its memory and found a precedent, found a piece of knowledge that enabled it to connect these two parts of the explanation. And so this link was formed, and the agent was then able to complete this explanation. This is an example how the learning goal was satisfied using some piece of knowledge. In this case, the knowledge came from the memory, but the agent could have potentially also acquired the knowledge from the external world. For example, it may have gone to a teacher and said, I have a learning goal, help me with the knowledge that will satisfy that learning goal. This ability to spawn learning goals and then find ways of satisfying or achieving those learning goals, or any goal in general, is another aspect of metacognition. So this was an example of how metacognition helps resolve a gap in knowledge. Now let us see how it can help resolve gaps in reasoning or learning. To see how metacognition can help resolve reasoning gaps, let us return to this example of using mean-sense analysis in the block's micro-world. Once the agent reaches a cul-de-sac in the reasoning, the agent could form a reasoning goal and ask itself, how can I help resolve this cul-de-sac? It may then be reminded of the strategy of problem reduction, which reduces these goals into several independent goals, and then the agent may go about achieving each goal one at a time. Thus, in this example, the agent set up a new reasoning goal and then used that reasoning goal to pick a different strategy and thereby achieve that reasoning goal. Note also that this is one way in which we can integrate multiple strategies. We first used mean-sense analysis, ran into cul-de-sac, formed a new reasoning goal, used that reasoning goal to pull in a different strategy, problem reduction, and then go back to the original strategy, mean-sense analysis, for achieving each goal independently. In this architecture for a cognitive system, we have drawn these boxes as if metacognition was completely separate from deliberation, and deliberation was completely separate from reaction. In fact, there might be considerable overlap between metacognition and deliberation. Some processes in deliberation might be viewed as metacognitive processes. Some processes of metacognitive might be viewed as deliberative processes. To see why the lines between metacognition and deliberation are blurry, let us return to this example from explanation-based learning. When we talked about explanation-based learning, we did not talk about metacognition at all. We can view the agent as saying, well, I do not know how to build a connection between this part of the explanation and this part of the explanation. Therefore, I'll set up a reasoning goal which pulls at some other knowledge and so on. Now that we know the vocabulary of metacognition, it is easy to view all of that in terms of this new vocabulary. So instead of thinking of deliberation and metacognition as two separate independent boxes, a better way might be to think in terms of boxes that partially overlap as a meta space and as a deliberation space. We should not be overly concerned whether something should go into the deliberation space or into the metacognition space. The more important thing is, what is the content of knowledge that we need to carry out a process, and what is the process that we need to carry out? In this course, we have learned about a large number of reasoning methods. Here are some of them. We could have added a lot more here, for example, planned refinement, or logic, or scripts. Typically, when you and I program an agent, we pick a method and we program that method into the agent. One unanswered question is, how might an agent know about all of these methods and then autonomously select the right method for a given problem? This is the problem of strategy selection, and metacognition helps with strategy selection. Given a problem, and given that all of these methods are available to the agent to potentially address the problem, metacognition may select between these methods using several criteria. First, each of these methods requires some knowledge of the world. For example, case-based reasoning requires knowledge of cases, constraint propagation requires knowledge of constraints, and so on. Metacognition may select one particular method depending on what knowledge is exactly available for addressing that specific input problem. If for that specific input problem, cases are not available, then clearly the method of case-based reasoning cannot be used. If, on the other hand, constraints are available, then constraint propagation might be a useful method. Second, if the knowledge required by multiple methods is available, then metacognition must select between the competing methods. Another criteria for selecting between these methods might be computational efficiency. For a given class of problems, some of these methods might be computationally more efficient than other methods. As an example, if the problem is very close to a previously encountered case, then a case-based reasoning might be computationally a very good method to use. On the other hand, if the new problem is very different from a previously encountered case, then case-based reasoning may not be a computationally efficient method. We have come across this issue of computational efficiency earlier in the class. For example, when we were discussing generate and test, if the problem is simple, then it is potentially possible to write a generator that will produce good solutions to it. On the other hand, for a very complex problem, the process of generating good solutions may be computationally inefficient. Similarly, if there is a single goal, then the method of means-ends analysis might be a good choice. On the other hand, if there are multiple goals that are interacting with each other, then means-ends analysis can run into all kinds of cul-de-sacs and have poor computational efficiency. A third criteria that metacognition can use to select between these various methods is quality of solutions. Some methods come with guarantees of quality of solutions. For example, logic is a method that provides some guarantees of the correctness of solutions. Thus, if this is a problem for which computational efficiency is not important, but the quality of solutions is critical, we might want to use the method of logic because it provides some guarantees of the quality, although it might be computationally inefficient. The same kind of analysis holds for selecting between different learning methods. Once again, given a problem, the agent may have multiple learning methods for addressing that particular problem. What method should the learning agent choose? That depends partly on the nature of the problem. Some methods are applicable to that problem, and some methods may not be applicable to that problem. Second, for example, in this learning task, if the examples are coming one at a time, we might use incremental concept learning. On the other hand, if all the examples are given together, then we might use decision tree learning or identification tree learning. Another criteria for deciding between these methods could be computational efficiency. Yet another criteria could have to do with quality of solutions. Now that we have looked at strategy selection a little bit, let us look at strategy integration. Even if the agent selects a particular strategy, it is not necessarily stuck with that strategy. As the problem solving evolves, it may well decide to shift from one strategy to another strategy. As an example, consider that for a given problem, metacognition decides to select the strategy of case-based reasoning. Now, case-based reasoning spawns a number of subtasks: retrieval, adaptation, evaluation, and storage. Metacognition can now examine the requirements for each of the subtasks. And then, for each of the subtasks, it may decide on some strategy. For example, for the task of adaptation, metacognition may pick the method of case-based reasoning recursively, or it may pick the method of rules to adapt a case, or it may use models for the case adaptation. If metacognition picks the method of rule-based reasoning, then note the metacognition has shifted from the method of case-based reasoning overall to the method of rule-based reasoning for a subtask of case-based reasoning. We can also use a similar analysis at the next lower level. Suppose that metacognition decides to pick the method of rule-based reasoning for doing the case adaptation. Now the question becomes what rule to apply, rule 1, 2, or 3. We can imagine meta rules that select which rule to apply under a given condition. We have come across the use of metacognition for strategy integration earlier. In this blocks microworld, we saw how mean-sense analysis can reach a cul-de-sac. When the cul-de-sac happens, metacognition may set up a new reasoning goal and select a strategy of problem reduction for resolving the cul-de-sac. When problem reduction then sets up 4 independent goals, we may revert back to mean-sense analysis to achieve each goal independently. In this particular case, we have integrated mean-sense analysis and problem reduction, and the reasoning has shifted between these two strategies in a seamless way. That's why we have talked about some of the uses of metacognition. We can use it to fix errors in knowledge or reasoning or learning. We can use it to fix gaps in knowledge, reasoning, or learning. We can use it for strategy integration. One thing that we have not yet talked about is what is the process that metacognition uses? What is its strategy? Well, metacognition can use the same kinds of reasoning processes that it itself is reasoning over. That is, case-based reasoning is a potential strategy for metacognition. Constraint propagation is a potential strategy for metacognition, and so on. Let us take an example. Supposing that metacognition comes across a problem and it must select among these strategies. Metacognition might ask itself, what strategy did I pick the last time I came across a similar problem? This is case-based reasoning at a meta level. To complete this example, metacognition might say, the last time I used constraint propagation as a technique for this particular problem, this time I'll use constraint propagation again. As another example, given a second problem, metacognition may use planning to set up a plan for using these various strategies, thinking of each of these strategies as an operator.
As a third example, metacognition might get a new problem and decide to use every single method at its disposal to generate a possible solution. It then might have some heuristics to test each one of those possible solutions and figure out which one is best. So then it's using generate and test to select between its multiple strategies.
To summarize this part then, metacognition can use the same reasoning strategies that we have been studying at the deliberative level.
So if metacognition reasons over deliberation, could we also have an additional layer where meta-metacognition reasons over metacognition? And to take that even further, could we have a meta-meta-metacognition that reasons over meta-metacognition all the way up, infinitely up in a hierarchy? Is this a good way to think about the levels of metacognition? So personally, I would say no, this is not a good way to reason over it. We talked about in the previous portion of the lesson that metacognition uses the same strategies that it reasons over. It reasons over case-based reasoning, it reasons over means-sense analysis, it reasons over problem reduction, but it also uses case-based reasoning, problem reduction, means-sense analysis, and the others to do that reasoning. So it really doesn't need an additional layer. It's already equipped with the ability to reason over case-based reasoning and the other methods, so it can just reason over itself.
This is really cool. So AI agents don't need multiple levels of metacognition because metacognition can reason over itself recursively. In fact, current theories of metacognition all talk about this kind of two-layered system between deliberation and metacognition.
So meta-reasoning can be very difficult to talk about because it's circular, so it's often unclear what exactly we're talking about at a given time. So to try to make this process more explicit, let's take an example. Let's imagine a robot whose task is to assemble a camera. And all day, every day, the robot sits there assembling camera after camera. Then one day, the boss walks in and says, instead of assembling that camera, disassemble this camera that's already been put together. So what does the robot do? It wasn't programmed to disassemble cameras, so how does it figure out how to do this task? Well, the robot might have a rule that says, given a new goal or given a new problem, choose the method for which I have the most knowledge. The robot might then look at its memory and say, well, the only thing I have is a bunch of cases of assembling camera after camera after camera. So this is metacognition. The robot has now thought about what it knows, it's thought about its new goal, and it's decided on a method to use to approach this new problem. But now that the robot has selected a method, it then needs to reason further. It's chosen case-based reasoning as its reasoning method. But how will it do the adaptation? Well, the robot might then select a rule out of its memory that says, to reverse a process, do the steps in reverse. So now we've done not only strategy selection when we selected case-based reasoning, but we've done strategy integration. That is now using a rule-based approach to take care of the case adaptation. So the robot uses that rule, reverses the steps, and disassembles the camera. Now the boss comes back by and says, well, yeah, you disassembled the camera, but why did it take so long? You could have done it so much faster. But the boss doesn't give any feedback as to how the robot could have done it faster. Then later, the boss brings back another camera and says, here, disassemble this camera, but do it faster this time. So now the robot needs to select a method again. It thinks, last time I used case-based reasoning to select my method for disassembling the camera. But case-based reasoning didn't give me an optimal solution. The boss complained that it took me too long. So instead, the robot chunks a rule that says, given a new task of disassembling a camera, suggest strategies other than case-based reasoning. So now it's used a form of meta-metacognition. It's thought about its metacognition. It's looked at the way it selected a strategy in the past and decided the way I selected a strategy in the past must not have worked because the strategy I selected wasn't ideal. So next time, select a different strategy. So here we've seen everything we've talked about today in action. First we saw using metacognition to resolve a gap. The agent didn't have any way of disassembling a camera, so it used it to select a strategy for resolving that gap. That's also strategy selection. It used case-based reasoning to decide what method it should use to resolve this gap. We then saw strategy integration, where it used a rule-based approach to adapt its prior cases. We then saw correcting mistakes, where the boss told the robot that it didn't do it fast enough, so its reasoning method must have been suboptimal, so next time it should try something different. That last part is also an example of meta-metacognition, or metacognition about metacognition. It looked at its strategy selection method and decided, next time I should select a strategy differently.
David's example of a robot that knows how to assemble cameras, but then is given the goal of disassembling a camera, is a good example of goal-based autonomy. Earlier we had looked at how an agent can go about repairing its knowledge or reasoning or learning when it makes a mistake or reaches a failure. But sometimes it is not so much that the agent reaches a failure as much as it is that the agent is given a new goal. When the agent is given a new goal, we do not want the agent to just fall apart. We do not want brittle agents. We want agents that can then adapt their reasoning methods and their learning methods to try to achieve the new goal, even if they were not necessarily programmed to achieve that goal from the beginning. We know that human cognition is very robust and flexible. You and I address a very large number of tasks, a very large number of problems, and achieve a very large number of goals. If we are to design human-level, human-like AI agents, then those AI agents will have to be equally robust and flexible. Metacognition provides a powerful way of achieving that robustness and flexibility. It does so by flexibly, dynamically selecting among competing strategies. It does so by flexibly and dynamically integrating multiple strategies as the problem solving evolves. It does so by using reasoning strategies and knowledge that were programmed into it to achieve new goals.
So like we said earlier in this lesson, we've actually been talking about kinds of metacognition throughout this course, even if we didn't call it that at the time. We were talking about agents reflecting on their own knowledge and correcting it when they were introduced to a mistake. Earlier in this lesson, we also talked about the possibility that an agent would reflect on the learning process that led it to the incorrect knowledge and correct that learning process as well. Back during partial order planning, we talked about agents that could balance multiple plans and resolve conflicts between those plans. This could be seen as a form of metacognition as well. The agent plans out a plan for achieving one goal, a plan for achieving the other goal, and then thinks about its own plans for those two goals. Then it detects the conflict between those plans and resolves that conflict accordingly. Then it detects the conflict between those two plans and creates a new plan to avoid that conflict. Here, the agent is reasoning over its own planning process. We saw this in production systems as well. We had an agent that reached an impasse. It had two different pitches suggested and it couldn't decide between the two. That spawned a new learning goal, to find a rule to choose between those pitches. It then selected a learning strategy of chunking, went to its memory, found a case, and chunked a rule that would help it resolve that impasse. In this case, the agent used that impasse to set up a new learning goal. It then selected a strategy selection, to achieve that learning goal. We can also see metacognition in version spaces. Our agent has a notion of specific and general models, and it also has a notion of convergence. The agent is consistently thinking about its own specific and general model and looking for opportunities to converge them down into one model of the concept. And finally, we can very clearly see metacognition in our lesson on diagnosis. We talked about how the results of our treatment become new data for our iterative process of diagnosis. If our treatment didn't spawn desirable results, it also spawns data for the meta layer. Not only do we still want to diagnose the current malfunction, but we also want to diagnose why we weren't able to diagnose it correctly in the first place. So now we're diagnosing the problem with our diagnosis process. So as we can see, metacognition has actually been implicit in several of the topics we've talked about in this course. So finally, to make things as meta as possible, meta-reasoning has actually been a motivating pedagogical goal for the design of this very course. You'll notice that for almost every lesson, we've started with an example of a problem that you could solve. In incremental concept learning, for example, we started by giving you several examples of foos and not foos, and then we asked you, is this a foo? In production systems, we gave you some information about a baseball game and asked you to decide what the pitcher should do next. In learning by recording cases, we gave you a world of rectangles and asked you to decide what color a new rectangle might be. In classification, we gave you a bunch of pictures and asked you to decide which of those pictures were birds. In planning, we gave you our blocks microworld and asked you to develop a plan to go from our initial state to our goal state. In each of these, we've started with a problem that we could solve that we then wanted to design an agent to solve. These examples then motivated our discussion not necessarily of how we did it, but how we could design an agent to do it. Then at the end of each lesson, we revisited that example. We took the reasoning method that we designed for our agent and looked at how that exact reasoning method would allow it to answer the same example with which we started the lesson. When you did the example at the start of the lesson, you didn't necessarily know how you were able to solve that problem. You could speculate, but you never know for sure. But then by building an agent that can solve that problem, we start to gain some understanding for the processes that we must be able to engage in order to solve that problem as well. So by designing the agent, we develop a greater understanding of our own cognition. So in this way, the very design of the lessons in this course has been driven by trying to develop metacognition in you. In fact, developing metacognition in students is the entire goal of my own PhD dissertation. So how would you use meta-reasoning to design an agent that can answer Raven's progressive matrices? Throughout this course, we've covered a wide variety of different methods for addressing this test, and each method has its own strengths and its own weaknesses. Certain methods are better for some problems and other methods for other problems. Meta-reasoning would tell us, though, that you don't have to choose just one. Your agent can have multiple methods to choose from. Discuss how you might design an agent to have meta-reasoning. What methods would it have to choose from? How will it evaluate a new problem and decide what method is best for that problem? How much improvement do you really expect to see in your agent's performance based on equipping it with meta-reasoning? And finally, will your agent engage in any kind of meta-meta reasoning, as we've discussed? Will it not only think about the methods themselves, but also about how it's selecting a method? And if so, how will that improve it even further? So today we've talked about meta-reasoning. This very strongly leveraged and built on nearly everything we've talked about so far in this course. Meta-reasoning is, in many ways, reasoning about everything we've covered so far. We started off by recapping learning from correcting mistakes and the related notion of gaps. Then we covered two broad metacognitive techniques called strategy selection and strategy integration. We then discussed whether or not meta-meta reasoning might exist, and we decided ultimately that such a distinction isn't even necessary. After all, the structures involved in meta-reasoning, like cases and rules and models, are the same as those involved in reasoning itself. So meta-reasoning is already equipped to reason about itself. Finally, we discussed a particular example of meta-reasoning called goal-based autonomy. Meta-reasoning is, in many ways, the capstone of our course. It covers reasoning over all the topics we've covered so far, and it provides a way that they can be used in conjunction with one another. We do have a few more things to talk about, though, and we'll cover those in our advanced topics lesson.
Meta-reasoning arguably is one of the most critical processes of human cognition. In fact, some research suggests that developing metacognitive skills at an early age in life may be the best predictor of a student's success later in life. Actually, this makes sense. Meta-reasoning is not about simply learning new information. It is about learning how to learn, about learning new reasoning strategies, about integrating new information into memory structures. Meta-reasoning is also connected to creativity. In meta-reasoning, the agent is monitoring its own reasoning. It is spawning goals. It is trying to achieve them. Sometimes it suspends a goal. Sometimes it abandons a goal. These are all part of the creative process. Creativity is not just about creating new products. It is also about creating the processes that lead to interesting products.